Very nice to meet you again.
Pleased to meet you.
Last time it was August,
Yes.
directly after COVID. And
So-
here now, June, about 9 months later. So
Yeah.
how are you?
I'm fine. Actually, I'm very glad that I can welcome you here at our laboratories of Karel Kolomaznik research team.
Yeah.
And it's a pleasure. I would like to introduce you what we actually do at an example of two projects which we are solving these days.
Yeah, I remember. I know the generality because of my last visit, but it would be good to refresh everything. So let's go. I follow you. Perfect.
So please welcome. This is our technological laboratory.
Okay. So this is organic waste recycling. We are in the organic waste recycling.
Yes.
So
that is-
recycling is a very broad field. Could be anything in the world, any materials, any. But here the specialty is organic waste materials. Could be any. But what we're speaking today is some of the specific materials they use. So you can explain what are the wastes that you are working with now.
Basically, in our research, we focus on processing of proteins. And as you said, we are to talk about protein waste. We have currently a project aimed at solving of industrial waste from sausage casings manufacture.
Sausage case manufacturing.
Yeah, it means it is a factory which produces casings for sausages, and during this manufacture, at several stages, protein waste is produced. Usually, it is a challenge, I would like to say, to find a sustainable solution
For this.
for
So
this.
this is a waste from a different part of the process.
Yes,
Of the sausage. So this is normally covering of the sausage.
exactly.
You know,
It is
when we buy a
actually
sausage
edible.
in the store, this is the cover. So this is organic material, and these are waste. So they are not off grades or any type of waste. And this is the same process, but it's coming from a different part, correct?
Yes, exactly.
Okay. So what to do with this? Okay. So one thing is these are waste material. You can landfill, which is not a good solution. So this is what we have here. They are processing this, correct?
Correct, exactly. That's
Processing, and what's the goal?
what's
to
the
produce?
goal? To produce an organic fertilizer.
So from organic waste to organic fertilizer, okay?
Yes.
And this is, I guess, this is what this is.
There are several possibilities how to process this waste. We can start with crushing of this waste before.
So this one,
Yes,
this one is crushed.
it is
To the-
crushed.
Okay.
However, I would like to focus, if I may, on
Okay.
specifically this project. We cooperate with Romania partners, company Probsdorfer, and also Footwear and Leather Research Institute division from Romania, and one Czech company. And our aim is to use any waste from sausage casing manufacture together. It means this
Could
type
be that
of
one,
waste,
this one.
this one, all together.
With
In-
together, together, these two,
or
both
to-
together. Okay.
Yeah, process in order to produce an organic fertilizer. It is currently being certified for organic farming because apparently it is of natural origin, of natural protein. It's like pure protein fertilizer. And we focus on maize treatment actually. The basic principle of our process is hydrolysis.
Hydrolysis, okay.
Which means that we take this protein, and naturally the protein is composed of very long molecules. What do we do in our process? We shorten the molecules, we seize them, if this is the correct word, and make them smaller, and after they are small enough, they do solubilize. It means that from solid waste, we obtain a liquid.
They become soluble to water.
Water, yes. And
So this is the key.
It's a key.
Cutting the long
Cutting,
molecules
yes.
to make them soluble in water.
Yeah. But this is just one part, because it is for a long time known that it can be done, and the challenge is to done it sustainably, which means economically in an economic feasible way.
Okay. Okay.
And also,
So what are the chemicals you use? Just the water?
No, this
What is the hydrolysis? Is at what temperature?
it's at moderate temperatures because we use an enzyme technology.
Okay.
Yeah, so it is enzyme technology. Here at this lab, we usually go from small scale. We have to perform many experiments to study the reactions and the processes and to
So the
optimize
process
the
of
process.
shortening the molecules.
Basically, yes.
Yeah.
Or if I put it very simple, it's how to cook this with no waste at the lowest price possible.
Okay.
That's
That,
how
that was my other question. So there is no waste here.
Yes.
All this produced is fertilizer.
Yes, yes.
And this is considered organic, semi-organic, fully organic.
Yes, we are able to produce fully organic fertilizer, or for, let's say, conventional agriculture, it is possible also to produce organomineral fertilizer. And you should hear more about it in another session with Professor Kolomaznik.
So this is kind of, if we vulgarize it, this is a long molecule, and you just cut them.
Yes.
You know.
It's
You know,
You are right.
And then make it soluble in the water
Yeah.
through hydrolysis at moderate temperature.
Yeah, yeah. It is just cutting. However, it shall be done wisely in order to
So you
cut
have
the
to
costs
you have
as
to
well.
determine the temperature, the parameters, the conditions. Correct.
Correct. And,
And this is the research.
and our aim is also to gain like purely organic fertilizer. It means that, for example, the ash content is very low. It means that it's just of natural origin.
Okay. Okay. So this is the lab part, correct?
Yes. This is the lab part where we start at small scale, and if
So here, what we are doing here. Here, you can say here. No, come. So, how are you?
How are you?
Hello, how are you? So, what we are doing here? You can speak, okay.
Yeah, I received some samples, then I am now filtering them and I will do some analysis.
Filtering from what? Filtering to remove what?
Remove some solid particles.
Oh, there are solid particles. These are samples of what?
I should say
it's samples for processing liquids. However, this is like, again, it's around proteins, but it's commercial research. So honestly, we cannot tell precisely.
Okay, that's sure.
I'm sorry.
Okay. No problem. And this is
This is storage tank. For example, in another part, we would like to show you our pilot plant. This is the main responsible person for the
Thank you.
pilot plant manufacture of the fertilizers.
Okay.
I don't think so, but I will show you. Well, so as Dr. Pecha mentioned before, so that's the pilot plant unit. So using this unit, we can scale up our technology. So to try or verify our laboratory technology, if it worked well. If yes, so we can then go to the industry and make it industrially.
So basically,
This is the reactor, main reactor. It has around 100 liters.
okay.
So the capacity.
The input of the reactor is what? Is waste.
Yeah, it's the waste, water, as
Yes,
George
same-
mentioned.
same percentage. Same
exactly. Same conditions, however, huge amount.
Okay.
So, and also because it's connected also with the vacuum evaporator. So if it's necessary to concentrate or thicken of the sample, so we can. So basically we need to evaporate the water from the product and make it more concentrated.
To concentrate the protein.
Yeah, the nutrients for the plants. Yes,
in
to
the fertilizer.
increase- Yes, in the fertilizer.
So
Exactly.
basically, it's a evaporation process.
Exactly.
And here,
This is just only for the separation of the reaction mixture. For also after the concentrating, it's possible to try to settle down the sediments, which is usually from the samples. So make it try to separate, and then we can get the final product.
This is the final product.
Yeah, the final
This is
product.
the fertilizer.
Yeah.
And Cortan is a commercial name or is it an internal name?
Yes, it's our cooperator in our project,
Okay.
Fertimate. So it's from the Czech part. It's coordinator from the Czech part.
And this is another reactor similar to that, or is different?
Yes, that's the same reactor, however, without the vacuum evaporator. So
Okay.
same conditions.
So
Same
tell me something. Going from the lab scale and coming here. So what are the difficulties? Is going smoothly, or you have to change things? You have to modify things from the lab to
Yes,
here.
of course. It's necessary sometimes modify because in the small laboratory amount, in case of our fertilizer, there is the problems because of the casings. It's as you see the small small casings so together. However, if we take it, so it has a lot of meat. And during the
So
process,
what is the
because
material, by the way? I don't know.
by the way,
This is what it is.
it's a pure collagen.
It's collagen.
You can say, yes.
Collagen.
Connected
So
together,
it's
basically.
eatable. I can eat this.
Yeah, you can.
Yeah,
So no
okay.
problem, because the
So-
sausage is
Yeah,
normal.
this is easy to cut the molecules here. The parameters should be easy here, no? I'm joking.
Yeah, and the problem
So, okay.
can be because immediately when we put it to the reactor and we need the mixture start to stir, and during the stirring, immediately the casting starts to grow because the air in the reactor and the water, so it starts to grow and it starts to make the problem with the stirrer. So that was the main problem during the scale up our technology.
So the
But
steering is a mechanical issue or?
yeah, steering. You can see the steering is an electronic steer.
So the problem was that it was. What was the problem with the steering?
I don't know how to explain. It start to, as you can help me to
I
go.
would like to with the word, but the thing is that the stirrer is like steering, so it the casings are tangled around the stirrer.
Okay, it's tangling. So it's a mechanical issue.
Yeah.
It's not a process issue.
If I may put it frankly, it is such a stupidity, but in reality, this is a big issue.
It happens. It's big
And it's a big issue because you cannot do anything with it.
I understand.
If there is this problem, and the technology must be able to solve it.
So this is the coming from lab to the pilot scale.
Yes.
And this happens all the time. That's why we're pilot scale. And then going from here to the industrial scale, what are the problems then? We're gonna see it tomorrow.
Yes.
Yes, or where basically regarding this problem because of trials at pilot scale, we were aware of this problem and prepared on it on the pilot scale. So at the blend scale test at the industry, it was solved already, and it was successful.
Okay.
It was necessary to
How
do
big it is there in the industrial scale?
10 cubic meters
Meaning
of water.
how much bigger than this?
This is 100 liters, so 100 times.
100 times more. So it's a big reactor. We're gonna see it tomorrow.
160 times.
Okay, so you have lab scale, pilot scale, and then industrial scale. We're gonna see it tomorrow. We're gonna put this. So this is the casing, the sausage casing.
Yes.
Then we go to we have another department or the lab.
We have another laboratories
Okay.
because actually part of the research as well as the part of the production is the detailed analysis of the products and intermediates. And
So you produce the fertilizer here.
Yes.
Different kind of fertilizer because of different parameters, different conditions. And then the other part of your work is to analyze how efficient they are. What are the parameters? Correct.
exactly.
What are the properties?
Exactly.
What kind of properties you measure?
We measure the protein content, like the organic
Okay.
part. We measure
Which is the most important one for fertilizer, correct?
correct.
The higher it is, the better.
Yes. Yes.
Okay.
And also it makes it's the reason why the fertilizer is good for the plants.
Okay.
Actually, why it works
Okay.
in a good and efficient way.
So
Then
protein
we
content.
measure elemental composition,
Okay.
which is also important from the safety point of view. in our case, we use food waste, so it's very safe. But in general, there can be, for example, heavy metals and so on. So we need to ensure that the product is safe,
Okay.
even from this
So you
point
check
of view.
elemental analysis. What are the dangerous products? A dangerous element.
Usually cadmium,
So I have to be
mercury,
low
and
as
so on.
possible.
Yes,
Otherwise, it will not be good for as a fertilizer.
exactly.
If it is higher, what do? You come back here and change the process, change the conditions.
We can do that actually, but to be specific in this case of food industry waste, it is not an issue because
Okay.
it is a food industry.
Yeah, it's already coming from food
Yes, so
components, so that this amount of critical elements are low
yeah,
already.
are low. On the other hand, other elements which are naturally present are important for the nutrition of the plants. So that is the reason why we analyze them.
Such as what are the most important for nutrition? We can go there and see.
Okay.
What are the most important ones?
So the most important one is nitrogen, phosphorus, and potassium.
Yes, which are
three.
the main fertilizers part. That you need nitrogen. Right?
Yes, we need nitrogen, and basically the protein fertilizer is like nitrogen fertilizer.
Okay.
But the effect, it can act as a biostimulant. We have a cooperation with Czech Academy of Sciences, and in many cases it was proved that this kind of fertilizer can act as biostimulants, which means that the plants are more tolerant to stresses. For example, dryness, if this fertilizer is applied.
Oh, okay.
So it helps them to survive even harsh
So
conditions.
it is a general purpose fertilizer. Can be used for any
Yes.
or specific for some.
In this project, we focus on maize or corn.
Okay.
However, it is a general purpose fertilizer.
Okay. So this is the way. This is the measuring of properties of the fertilizer produced. Chemical properties, physical properties. I don't know if you measure viscosity. You measure viscosity also because for the distribution in the field, correct?
Yes.
The viscosity and what else? Chemistry. In physical properties, what do you measure?
pH is important.
pH. What else? This is chemical. What about physical?
Well, okay, dry matter content, for example.
Oh, diameter.
No diameter, but the dry matter content.
Oh, dry.
Humidity.
Oh, humidity. Okay, humidity. Okay. So, you are calling Juan Carlos?
No. I'm calling my colleague who is responsible for measuring of the length of the molecules, actually.
Oh, okay. But anyway, while he comes, we can see this one here. Correct. So here you measure
Here's the machine for nitrogen measuring.
nitrogen measurements.
Gas
So-
chromatography detector.
So you measure the composition of the gas or just the
No, just the overall content of the nitrogen.
nitrogen?
Yeah.
So this is total content of nitrogen, but you
Yes.
burn the sample and you
It's burned.
it's burned 100%, I guess.
Yeah.
And then you measure how much nitrogen it is in
Yes.
the gas, which reflects how much hydrogen it is in the fertilizer, correct?
Yes.
It's 1-to-1. It's 50% there, 50% there, whatever it is the same, correct? Because it's burned completely,
Yeah, it's
and the composition of the gas is the same as composition of the nitrogen in the fertilizer, correct?
Yes.
Okay.
Mhm.
Okay.
Exactly.
Okay. And then what else? So we here it is nitrogen content. What else you measure? You mentioned chemistry. You mentioned physical properties.
And that's all. We don't measure it here, but our partners, of course, measure performance of the fertilizer on plants
Okay.
because the project is aimed at maize. So they follow their growth at greenhouse, but even field conditions, which means that we had to prepare larger samples for field tests.
Okay. But the machines here are measuring what?
Well,
Is chroma service.
in our team, we are doing a lot of different things. So one big group of our research is protein-oriented, which we are currently talking about. And the second large group is lipid or oleochemistry oriented.
Okay.
And most of the time we use these machines for the oleochemistry research. Like for example, as an example, we developed a technology for turning of waste fats into biodiesel.
Okay.
And here we were assessing.
So this is important. You are
Biodiesel.
changing fats to biodiesel.
Yes.
Okay. This is. And then what do you measure here? You measure the property.
Property of the input lipids
Okay.
and final products
Of the
which are
biodiesel.
the biodiesel. Yes.
So what do you measure exactly? What
Exactly. In here we measure the content of alcohols,
content of alcohols.
and in here we measure content of biodiesel,
Biodiesel. Okay.
and also the content of impurities, which is the unreacted lipids.
Oh, okay. And the same thing here.
The same thing here, but here is like a small mass spectrometer,
Okay.
which can apparently or tell us not like about or identify the compounds which are measured. For example, if there is some
So
impurities.
this is a different project.
Yes, this is the different project.
Okay, but still using waste to produce biodiesel, right?
Yes, but the challenges are still the same in order to find out or design a sustainable solution,
Yeah.
which is technological and economical viability. So,
Here we have a spectrometer. Yeah.
and colleague will tell
Hello,
you more.
how are you?
I'm fine, thank you. This is X-ray spectrometer, X-ray fluorescence spectrometer. This is able to measure elemental composition of anything, of liquid, of powders, and we are able to measure from sodium to wolfram, let's say.
At this particular moment, what the sample is what?
This is fertilizer.
Fertilizer. Okay,
Yeah,
this is the
we
fertilizer.
we can
the
say
one you
that-
mentioned, correct?
Yeah, yeah,
Yeah.
yeah. And we can say that there is some.
So this is
Sulfur.
elemental. How many elements you can measure in total?
In total, from sodium to wolfram, let's say it's around 100.
Oh no. Okay. So this is elemental composition that you were speaking about. You have to make sure that the cadmium and undesirable elements are still safe, are correct.
Yeah, exactly.
And then these phosphorus, nitrogen, etc. Should be at the right optimum content, correct?
Exactly.
But does the nitrogen content here agrees generally with the
Here-
nitrogen
here we
content
are-
there?
Here we are able only from sodium,
Okay.
because nitrogen is 7.
Oh, okay, so you cannot measure nitrogen here.
No, from sodium 11.
Okay. So the red color there you cannot measure.
We are able from sodium and more, like aluminium, phosphorus, sulfur.
So
and
the
so on.
two-step process. There you measure nitrogen, and
Yeah,
then
exactly.
here the rest. Yeah, excellent. And this you mentioned about
Yes, that we need to measure the length of the molecules, which is done here. My colleague is responsible for this part of measurement.
Hello. How are you?
Hello, how are you?
So tell us how you measure the molecules. Well, where is your meter?
So our meter is
No, I'm
HPLC
joking.
with,
I need the physical meter to measure the molecules.
so I will show you our physical meter.
Oh, you have it? I was joking.
Yes, this is our meter.
Okay.
Okay. So when we put it inside,
Okay.
we can measure using this HPLC and gel permeation chromatography the molecular weight of different biomolecules, hydrolyzers.
Okay.
Okay.
So what is the length? What is the longest molecule you can measure here? What's the longest side?
It depends on biomolecules. So when we talk about, for example, hyaluronic acid, we can measure 1 million Daltons. And
So what is Million?
1 million
1 million
daltons.
daltons?
Uh-huh.
Okay.
And regarding protein hydrolysides,
What about
it's only about 1,000
1,000.
daltons.
So what is the shortest?
The shortest, it's
Approximately.
500
So,
daltons.
so when you get the protein here and it is longer than needed, what do? You go back there to the process? If the length of protein is not as short as you want,
It depends whether we are talking about research or like control of,
okay.
let's say,
So
plant
you're
tests.
determining
Yes.
it is a fundamental issue or it is a process issue.
Both. If we are talking about the plant scale, we need to ensure that the process works still well, continuously and constantly. So we just verify and check that it is normal. But in our research part, we study the reaction at which conditions or how the reaction conditions influence the length of the chain.
So the goal is the length should be the smallest possible.
I would
Or
say
there is an
small
optimum.
enough.
Small enough, which means what?
Which means in the project Fertimase we shall obtain considerable portion of fraction lower than 600 daltons. Which means that there shall
If
be.
it is smaller, then what happens?
If it is smaller, it more easily penetrates inside the plant. So that's the purpose.
So the goal is smallest possible. But you told me optimum.
That there is optimum. It is not as small as possible. The
Because
thing is,
that's why my question. Why is not the smallest possible the best?
because it's too expensive.
Oh, okay. That's a different story. So we're going to sustainability. Thank you. Thank you. So you have to have a small size molecule to be economically feasible.
Yes.
Okay.
We can talk about this
Yeah.
in this way.
Yeah,
How
yeah.
to
No,
understand.
that makes sense. This was the reason I was asking. This one here. What do we have here?
This one here. Here we have another example of the waste with which we work. This is a waste wool. It's completely raw. It's from organic farming, so you can see all the dirt inside. Like there is everything. It's just really raw wool. And
So this waste become your primary material to produce what?
we produce
It's too strong.
fertilizer,
Yeah.
which is for organic farming from completely organic feedstock, which
Okay.
is important.
So basically, from this, you get this.
Yes,
This is purely organic fertilizer.
yeah, it is. I will now speak more chemist. This protein is keratin.
As a keratin.
Usually, if you put our bodies into the ground, our hair lasts there long time.
Exactly.
So it is a problem to
Dissociate,
destroy
this.
like visibly
Yeah.
this type of material because it's quite durable. We are, I would say, proud that we were able to develop and design technology which is able to hydrolyze, to
Still, we are
solubilize.
speaking hydrolysis,
Yes, we are still speaking about
but
hydrolysis.
at different conditions.
Yes, at different conditions because this feedstock is much more durable.
Okay.
It's quite hard to obtain liquid fertilizer from it.
So what is the ratio to produce this? How much you have to produce? How much do you have to use?
Well, if we measure
This is 25 milliliters. Right?
the weight, so let's say, I don't know, we have here 25 milliliters and 30% of it is this wool
Okay.
on weight.
So 30% of this is weight. So how many you need? How many? With all different questions. With this bag, how much of that you can produce?
Yeah. Okay.
Let me put this back in.
If I weigh it,
Yeah.
let's say if I take 1 kilo of wool,
Okay.
I'm able to produce nearly 3 kilos of this fertilizer.
One kilo,
One kilo of wool, nearly 3 kilos of the fertilizer.
because you put other components in.
Oh,
How come one kilo becomes 3 kilos?
The rest is water.
Ah, the rest is water. Okay,
Basically.
but pure water.
Yeah.
Product of hydrolysis
Yes.
at specific conditions.
Our aim, we use like pressure process. Most of the auxiliary agents are recycled in the process. And again, the main challenge was to do the process economically viable.
Okay.
That was one big challenge. And also environmentally friendly, because it is possible to solubilize the keratin, but usually you need to use a lot of harsh chemicals which remains inside there.
And in this case, you don't.
We don't use it.
And with the classical process, what chemicals you use?
There are several approaches, but for example, strong alkalis are there,
Okay.
which can be used as well. They can be even good in the fertilizer. But in that case, a lot portion of the fertilizer or high portion of the fertilizer is composed of these added chemicals. And in our case, we have basically pure protein. Also, keratin hydrolysates are used, for example, in the cosmetic industry for hair shampoos and so on, because they...
So 1 kilo of this with water becomes 5 kilos.
3.
3 kilos. 1 to 3.
1 to 3. Yeah.
And then this 3 can be used for how, what's the surface in the field. So now we are coming to the efficiency and to the
Yes.
economics. So this is probably this is probably something that we can explain. We can have a seat here and we can explain the economics now.
It depends. That's a very good question, because there are two views on it. If we use it as a pure fertilizer, we need to put very much nitrogen of the field. So in that case, we need hundreds of kilos of this fertilizer.
For 100 kilos
For 1 hectare during the year.
100 kilos for 1 hectare per year.
Per year.
100 kilos per year per 1 hectare.
Per 1 hectare.
We are speaking for any or maize, only maize or...
This is not focused on maize.
This is just general.
Yeah, it is general, and the people from the agriculture, they know how much nitrogen needs potatoes, how much nitrogen need different plants, so they adjust.
Okay.
But it's hundreds of kilos. However, and in this case it is quite expensive. However, if it is used as an auxiliary fertilizer, because our main aim is that it is soluble, so it can be used as a leaf fertilizer. In such a case, we use from 1, let's say, to 6 liters or kilos per hectare per year, and it is possible to increase the crop yield about, let's say, 10 or 15%.
15%.
Which is interesting.
This organic fertilizer. But what's happening with the normal fertilizers, the classical one? How you can compare the classical one with this one?
It is different because it can be used in organic farming. Like many conventional classical fertilizers, like urea, you cannot use it in organic farming. Because from the definition, the organic farming is based on the idea that natural product shall be used during the farming, and this fertilizer is a natural product, it is not synthetic.
But what's wrong with the synthetic ones?
Some of them do deteriorate the quality of the soil in some manner. So this is a way how to improve the soil. However, our primary aim was to turn this kind of waste into something useful. Because if we are talking about the keratin, protein, it is not just a wool, it is, for example, feathers. In slaughterhouses, tons of feathers are produced. So, so that's the potential.
Sure, I understand the issue is the comparison between classical fertilizer.
Yeah.
In terms of price, in terms of cost, how you compare with, because it's organic, how you compare with the normal fertilizer? Classical one, which is not organic.
It is more expensive.
But efficiency in the field? It is higher, lower compared to the other?
Sometimes the quality of the product can be higher because, for example, if we are talking about the nitrates content in the food, some tests which Professor Kolomaznik done in the past proved that if you use conventional fertilizer, nitrate type, you got nitrates in your food. In this case, there are no nitrates. And we have good experience with the farmers who were able to cure their plants. Because of this fertilizer, it can act as a biostimulant, so it's an added value, this functioning.
So is it a field for research to decrease the cost? And the cost, the main cost comes from what? What's the factor that increases the cost? Because it's organic. Why it is higher the cost compared to the normal fertilizer?
Well,
So I mean, can this compete with the normal fertilizer?
actually, I don't think so. It is good as a combination that it has some unique properties.
Okay.
But apart from organic farming, the conventional or synthetic fertilizers are like economically better because basically they are produced from air.
From just normal organic waste.
No, from nitrogen, from air. Like urea is produced from air.
Oh no, I understand. But no, yeah, this is the classical fertilizer,
Yes,
right?
yes.
Yeah. But this one, it is just from organic waste.
Yes, it's from organic waste. And for example, in our country, there is a problem that the animal farming goes down, and in the soil there is not enough of organic matter. And this is a way how to turn at least.
And do you need always organic matter in the soil?
Yes.
If you have a classical fertilizer?
It's good for the soil. Like you do not need it like only organic, but the soil needs an organic part. And for example,
So you mean the fertilizer, the classical fertilizer, which is not organic, cannot replace 100% the organic fertilizer, right?
yes.
What is the percentage in the field?
I don't know because honestly, I'm a chemist.
I understand. That's okay. This is agriculture question.
Yes.
Okay. Well, very interesting. So all this, what type of other ways you treat? You treat the shoes.
Yes.
You treat what else? Which one is organic waste? You
Basically,
okay, the question is to finalize. Which organic waste you cannot treat?
which is not from protein or waste.
Which is not from protein waste.
Or waste.
So
sorry,
a waste that
protein.
doesn't contain protein.
Yes.
But if it is organic, it should contain protein all the time, or not?
No, because organic can be, for example, polysaccharides like sugar or cellulose.
Without protein.
Without protein.
So you are able to treat all protein-based organic waste.
Yes, let's say.
Protein-based organic waste. And to produce fertilizer, organic fertilizer that the land needs, despite that you can lose a major part of the classical fertilizer.
And which makes sense even economically as an auxiliary leaf fertilizer.
Mm-hmm.
In this scheme, it works, I would say, perfectly.
So, any organic waste, even from humans, or no?
Even from humans. If there is a protein, we are able to.
You are able to.
make
Okay,
it.
that's it.
Because that's our focus of our team. It's not only waste, but let's say protein processing in general. That's our focus.
Yeah. Well, then we went too deep into scientific field of treating human protein. What about human protein?
Which one?
I don't know.
Hair? No problem.
Hair, yes.
Skin?
Skin, you can do it.
Yes.
And you turn it on fertilizer. You are circulating the natural products.
Yes.
Well, this was a very interesting, visit. So we have here organic, protein-based organic waste treated to produce fertilizer to make it cyclic from organic waste to organic product or to organic, from a organic waste to an organic product. It can be used in the field to produce and go around, which goes to the grass, goes to the sheep, and basically we have a type of circular economy in the protein-based products, protein-based waste. I mean, well, I have to correct myself. So we have a circular economy in organic materials. In this case, only those that contain protein, correct?
Yes.
Not the others. Okay, it's a pleasure. It's very interesting. I wish you success to increase the number of protein-based waste from humans, from animals, from anything. And then when we meet next time, you're gonna present probably in CIPS some of your technologies. So it will be interesting. And people are invited, all those that are interested, to have organic fertilizer that have various advantages compared to the classical, non-organic fertilizer. They are welcome to participate at this symposium, which is by not so chance dedicated to Professor Kolomaznik. The laboratory will keep his name. He has a long time contribution in these technologies, and Jiri will be in charge, I guess, as a head of laboratory in the future. So I wish you success and continue with a good job.
Thank you very much.
It's a pleasure, and I look forward to your presentation in CIPS.
Yeah, I look forward to meet you there.
Sure, it's coming in November. Okay then, so I wish everybody that is looking a good day if it is in Europe, or good morning in North America, or good evening in Asia, and see you all in CIPS, Phuket, Thailand, 27th of November to 1st of December 2022, in person, not in Zoom.